Just take a look around you for a second. The building you're in, the sidewalk right outside, that bridge you probably drove over this morning. It's all built on the silent foundation of our world, concrete. And you know, we see it as permanent, right? Rock solid. But in reality, it's fighting a constant, invisible war for its own survival. It's a hidden battle for durability, and we're about to go right to the front lines.
It's a pretty terrifying thought, isn't it? But this isn't science fiction. The long-term integrity of our entire infrastructure, everything from dams to skyscrapers, it all depends on winning this battle. The stakes could not be higher, because the strength of our concrete is, quite literally, the strength of our civilization.
So, in this explainer, we're going to uncover the whole story of this fight. We'll start by looking at why the cracks are even beginning to show. Then we'll meet the villains, the forces trying to tear our world down. We'll also introduce the scientific heroes building a stronger defense and see how we're learning to predict the future, all so we can design for a century and beyond.
Okay, let's start with the core problem. For all its strength, for how tough we think it is, concrete has this hidden vulnerability. It's not immortal, and the forces of nature are working to break it down from the very moment it's poured.
And look, this isn't about some sudden catastrophic collapse you see in the movies. It's a slow, relentless process of degradation, a war of attrition that's fought on a microscopic level. It's happening right now, inside the very structures we depend on for our safety and our whole way of life. So who are the attackers in this invisible battle? To really understand how to defend concrete, we first have to understand its enemies. And you can think of these as the primary villains of our story, the forces that are constantly probing for any weakness they can find. Enemy number one is corrosion. You see, most big concrete structures are reinforced with steel bars. Think of it as a rebar skeleton. When moisture and chemicals manage to get inside, that steel skeleton starts to rust and expand, and that cracks the concrete from within. It's the ultimate inside job, and the research is clear, it's a primary cause of durability loss.
But wait, if that steel skeleton is protected, how do these corrosive things even get inside? Well, that brings us to our next set of villains, the chemical invaders. They act like spies, basically opening the gates so corrosion can just march right in. The very carbon dioxide in the air can seep into the concrete, and that changes its chemistry in a process we call carbonation. At the same time, salts, from de-icing roads in the winter or from seawater, they can penetrate the surface. Both of these invaders break down concrete's natural defenses and throw the door wide open for that internal corrosion to take over.
And finally, you've got the brute force of the elements themselves. Just picture this. Water seeps into a tiny crack. Then it freezes, it expands, and it forces that crack just a little bit wider. Now repeat that cycle hundreds and hundreds of times, and you've got major damage. Add in the extreme stress from something like a fire, and you have a recipe for structural weakening and this thing called spalling, where the surface layer of the concrete literally just pops or flakes right off.
So here's the crucial point. These enemies aren't just causing a little cosmetic damage. They lead to a real reduction in strength. They weaken that critical bond between the steel and the concrete, and ultimately they compromise safety and lead to billions upon billions in costly repairs. So, how do we fight back?
Well, this brings us to the heroes of our story, the material scientists and engineers who are forging a stronger shield. And they're not just patching up old concrete, they are inventing entirely new kinds of it.
And the leap in performance here is just incredible. On the left, you've got your traditional concrete, with all the vulnerabilities we just talked about. But on the right, you have these advanced materials like ultra-high performance concrete and geopolymer concrete. These are fundamentally different. They're designed from the molecular level up specifically for durability.
Let's just quickly look at how they work. Geopolymer concretes often use industrial waste products to create a chemistry that's just naturally more resistant to those chemical invaders. Then you have ultra-high performance concrete, or UHP. It's packed so densely and filled with these tiny steel fibers that it's not only incredibly strong, but also more flexible. And then you have innovations like adding nanosilica. These are microscopic particles that literally plug the pores in the concrete, creating a barrier that water and salts just can't get through.
But building stronger materials is only half the battle. We also need to get smarter. We need to be able to look at a bridge or a building and actually predict its future, to see the damage long before it turns into a disaster. And believe me, this is a huge challenge. Concrete is a really complex, messy material. Predicting exactly how and when it's going to fail under years of stress from weather and chemicals and loads, it's incredibly difficult. But this is where data science and artificial intelligence are completely changing the game. This number right here brilliantly illustrates the power of that new approach. This R-squared value of 0.91, it comes from a recent study. Now, in simple terms, it means the machine learning model was able to explain over 90% of the variability in the concrete's properties. That is a stunningly high level of predictive power, and it replaces slow, expensive physical tests, giving engineers this powerful new tool. And beyond just prediction, we're now giving our structures a nervous system. Researchers are embedding fiber optic sensors directly into the concrete as it's being built. So when a microscopic crack forms under stress, it causes this tiny, measurable change in the light that's passing through the fiber. An AI system can then analyze this data in real time to pinpoint the exact location and severity of damage, long before it would ever be visible to the human eye.
So let's put it all together. When you combine these advanced materials with this kind of smart monitoring, you don't just get stronger concrete. You unlock the ultimate goal: designing infrastructure that is not only durable, but also sustainable.
So what's the payoff? I mean, what does this actually get us? This is where it gets incredibly compelling. A case study on that ultra-high-performance concrete found that because it lasts so much longer and needs far fewer repairs, it can lead to over 40% in cost savings over the structure's entire lifetime. And because you're using less material and doing less maintenance, the environmental benefit is massive. We're talking up to a 76% reduction in toxicity impacts. Building to last is also building green.
Ultimately, this is the key takeaway. It's not about one single magic bullet. It's about the synergy, that powerful combination of creating better materials, using intelligent models to predict their behavior, and adopting a mindset that prioritizes long-term durability and sustainability from day one. And that leaves us with a final thought. We've seen the enemies, we've met the heroes, and we've seen the incredible new tools at our disposal. The secret life of concrete is, well, it's not so secret anymore. So the real question now is, armed with all this knowledge, how will we choose to build the world of tomorrow?